Hi everyone, and welcome to today's webinar entitled Green Solvents, Design, Selection, and Commercial Use. My name is Laura Hoke, and I'm a technical fellow here at the Green Chemistry and Commerce Council. For those of you that are not familiar with the GC3, I just want to give you a little bit of background about who we are and what we do. So the GC3 is a cross-sectoral business-to-business network of over 120 companies and other organizations. We were founded in 2005, and our core mission as an organization is to collaboratively advance green chemistry across sectors and supply chains. So this is just an example of some of the member companies that we work with. So you can see here from all the logos, this is by no means an exhaustive list, but you can see here that we work with a variety of different companies from multiple points throughout the value chain. So from chemical manufacturers to retailers to brands, to many others. And we're really grateful for all of these voices and companies and organizations that do come to the table to work with us as we try to mainstream green chemistry. So I want to give you a little bit of background about today's speaker. So we're very lucky to have Carlos Esteves, who is the co-founder and vice president of R&D at Inchemia. His research at Inchemia has been strongly focused on green chemistry, in particular the design of safer and more environmentally benign functional products. This includes the design of safer solvents for a variety of industrial applications, which we've asked him to speak about today. So I just want to say thank you to Carlos for joining us to talk about his company's unique approach to finding safer alternative solvents. So we're really excited to hear Carlos speak. Before we begin, there are a few ground rules I just want to bring to your attention. Due to the number of participants in the webinar, all lines will be muted. If you have a question or comment, please type it into the questions box that's located on the control panel to the right of your screen. And then we'll have a question and answer session at the end of the presentation. So with that, I would like to turn the controls over to Carlos to tell us more about his work. So Carlos.
Thank you very much, Laura, and welcome to everybody. Let me start saying the green chemist's dream is a world economy driven by non-hazardous chemicals that preserve the environment in its natural state. It's an exquisite dream, and I hope to persuade you that such economy can be gradually attained. And I want to thank GC3 and in particular Laura Hoke for giving us the opportunity to share with you our vision and to explain some examples of solvent replacement initiatives that are of industrial relevance. To drive the economy with green chemicals means fulfilling all the functions existing in the economy. A function in the economy context is a desired effect that brings a property or creates a necessary condition to goods, the environment, or people. This is how we understand a function in economy. For example, refrigeration. It's the function that accomplishes food conservation, is enabled by chemicals such as chlorofluorocarbons. Another function would be crop protection. Crop protection is possible through the use of agrochemicals, pesticides, fungicides, herbicides, and other products. Surface protection against ambient degradation could be another important function of the economy. We use paints, varnishes, and other coatings for protecting wood, metals, plastics. Lubrication, for example, is needed to minimize friction and wear. And in the cosmetic field, one very known function is, for instance, a skin protection against UV light, right? So I leave now the concept of function for a while to address another central concept in green chemistry, and it's what we understand by a green chemical in the context of industrial application. Since chemicals in economy perform functions, as we have already seen, any chemical, including green chemicals, should display the desired level of performance and functionality, at least in one function. I think we can all agree on that. And I know the definitions is something always tricky in science and technology. But we have adopted as a general definition the one given by our colleague, Dr. Paul Anastas, who is professor of green chemistry at Yale University. He says, a green chemical is one that provides higher performance or equal performance and functionality while being more environmentally benign throughout the entire life cycle. So this approach was codified in the famous 12 principles of green chemistry, which provide a framework and for innovation and design. But we as green chemist practitioners in laboratories, we need a more operational definition when we think, you know, an application chemist trying to find an optimal green chemical substitute or replacement in their efforts of developing a product formulation or process. Now, one way to define a green chemical is through the use of existing and well-known indicators or parameters that are common for the global chemical community. The global harmonized system is a codification system that informs about the toxicological and safety endpoints of substances. You all know. Based on standardized laboratory tests, there are 34 health endpoints, 8 environmental impact categories, and around 24 safety parameters. Each one, you know, is coded by an H number. And a chemical substance that is labeled with a given H number, then it's characterized by the specific hazard encoded by the H number. Based on global harmonized system codes, the column model classifies chemicals in 5 different categories, from negligible hazard to very high hazard. For example, a mild irritant would correspond to the low hazard level. A chemical causing cancer would be a chemical of very high hazard, very high concern. So here in green chemicals, our basic selection criteria allows the use of substances displaying negligible, preferentially negligible or low hazard according to the column model. Now, of course, exposure routes and risk scenarios matter when it comes to the use of chemicals in economy. So, for example, a substance without the ignition hazard could be safely used for instance, a cosmetic application, while it would be dangerous if used in automobiles. So in few occasions, there are conflicts between properties. We may allow for certain compromises between environment, health, safety variables, but our preference is to select and filter only those chemicals that are negligible or low hazard according to the column model. There, of course, are other environmental parameters that might not be included in the global harmonized system, possibly the tropospheric ozone potential. So we add those environmental health and safety parameters not accounted for by the GHS system as additional selection criteria. Now, I would like to introduce a third important notion, It's called diversity, and in particular, chemical diversity. To illustrate this concept, let me introduce you the Inchemia Solvent Library. So, over the past 20 years, we have put together an ensemble of chemicals with solvent properties. It contains today more than 300 solvents fulfilling the Inchemia environmental health safety criteria, and it's growing. You may ask why we have created this relatively large ensemble of green chemicals. What are the defining features and why is it important? Let me start answering the first question. When it comes to green solvents, we need to create a minimum diversity in order to enable application chemists and industry to achieve the functional performance of the commercial product she or he is developing. I will come back later to the relationship between diversity and function, because I think it intensely matters to green chemistry practitioners. I would like now to tell you one thing about the number of chemicals we use in commercial scale. I find it stunning. The world economy functions with approximately 1,500 solvents. At least this is the number of solvents, the solvent entries you find in the Handbook of Industrial Solvents. So compare this number with the solvents that may theoretically exist, ignoring for the moment synthetic accessibility and economic constraints. Ask, for example, how many isomeric alkanes with 10 carbons exist. Morowitz, who studied the origins of life, found that there are 75 isomers. This number rises exponentially to 360,000 for alkanes containing 20 carbon atoms. Make again the computation, replacing carbon atoms in the alkane molecular structure by heteroatoms and their combinations. The combinatorial explosion that occurs leads to a massive number of potentially existing solvent-like chemicals. So probably several orders of magnitude larger than the substances listed in the chemical abstract registry, which is 1.3 times 10 to the 8th power. This, I think, has a profound physical meaning. We can sustain the economy with a subset of chemicals that is grotesquely inferior than the total number of possible chemicals. Therefore, if the library of 1,500 existing industrial solvents has not been assembled by chemists and technologists by selection of the most fitted solvents from a pool containing the complete set of solvent-like molecules that can exist in the universe, then the origin of the non-industrial solvents responds to alternative innovation processes. Certainly, many solvents in the Handbook of Industrial Solvents have come to exist after the discovery of a new synthetic process or reaction. Other solvents came into place by exploring what the theoretical biologist Stuart Kaufman denominates the adjacent possible. For example, the expansion of a class of solvents through the synthesis of structurally chemicals of the homologous series is an example. A significant fraction of the existing solvents were brought to existence by chemical design as well, just to achieve a specific functional performance or cover a gap in the physical chemical parameter space. These are called designer solvents. So we reach now an important conclusion, I think. The emergence of new solvents in the history of chemistry enabled the appearance of new functions and chemicals. New functions prompted the design of novel solvents in turn, and more solvents enriched the context, ultimately opening new opportunities for new functions, new chemicals, and new solvents. So solvents and functions have in a way, co-evolved in common technological trajectories across different sectors in the economy. I ask now three questions. How can we design libraries of green solvents aimed at replacing solvents with undesired environmental health safety properties or its application in well-established functions? In particular, what should be the size of that library? What should be the optimal diversity of such library? My second question is can a library of green chemicals have any important role to satisfy the complex functional requirements of industrial products and processes? And the third question is, can such a library actually come to exist at all? Now, to the best of my knowledge, there's no law or theory in physics or chemistry that can give us an answer to these very deep questions. My goal here is to bring to your attention what it can constitute the starting point of a body of knowledge that will help us understand these very fundamental questions. I will present now the Inkemia solvent library, and later I will show how we have used it in a number of case studies. So the Inkemia solvent library is composed of more than 300 pure solvent candidates. There are existing commercially available solvents. There are novel solvents never used in industry at large scale. Of the total number of solvents, so we have measured and predicted many properties. We have also measured experimentally or predicted using computational algorithms. So we have assured the desired diversity by using more than 30 building blocks or chemotypes, and we have built variants around these building blocks. Now this is the very basic information on the library. So let me say about the molecular structure of its constituents. As I mentioned before, the library has been optimized in terms of its environment, health, and safety properties by the structure property similarity principle. This particular characteristic of the library, being optimized in terms of the sustainability properties, has consequences on the molecular structures that we have selected. And this is illustrated in this plot. This plot is a principal component plot that compares 96 structural features for the set of traditional solvents, and it compares with the set of Inkemia solvents. Each dot in the plot corresponds to one solvent. Red dots are traditional solvents, the most used traditional solvents. The blue dots are Inkemia solvents in the Inkemia library. Now, according to the similarity principle, the set of green chemicals should display similar properties than the traditional set of chemicals, those with, in principle, undesired EHS profiles, in order to keep the functional variables. We will talk later what is it, but you now feel that the functional variables is those that determine the efficacy of the chemical product doing the function, accomplishing the function. So in order to keep the functional variables within bounds of efficacy, so any alternative, any chemical structure should not depart largely from the original structures. However, by the same similarity principle that states that the chemical structure of the green alternatives should be significantly distant from the traditional set if we want to get rid of the hazardous properties. And this is a fundamental conflict between properties that we need to carefully manage. Otherwise, the similarity principle may pose important barriers for use and ultimately for market penetration of the greener alternatives. So you can see in the plot how the majority of solvents lie close to the x-axis, which is the first principal component. This reflects a similarity of properties, meaning that all our liquids may be similar polarities, similar functional groups, similar connectivity indices, similar topological indices, all the features that characterize this molecular structure. However, you can see that there's a clear distinction in the distribution of red dots versus the blue dots, the traditional versus the Incemia, with only a small overlapping region. So there is a difference, but not much difference. So in essence, we would say a good library should exploit small molecular structural differences to maximize the absence of hazardous properties while keeping the functional properties as close as possible to the traditional set. Now this is just a comparison of the traditional solvents library with the Incemia solvent library according to the column model in terms of the health hazard. So now how the distribution of solvents in the Incemia library, the plot at the right of your screen, is predicted centered on the negligible low category. It's the blue and the green sectors. This is compared to traditional solvents, where almost 3/4 of all of them fall on the moderate to high to very high hazardous levels. So here is a plot that summarizes the distribution of solvents in the other categories of impact, like the aquatic toxicity, the VOC, emission potential, flammability, and occupational exposure. So, now let me introduce at this point so some examples of application of the Incemia library to solve a number of industrial problems, and we will come back later on with more theoretical grounds and information, just linking the function and diversity. But let us now focus on examples of application. Let's see the library in action. This is the first case. This is a cosmetic challenge. This is the goal of the project was to find a safer solvent for a rinse-off cosmetic formulation. The formulation had to meet 7 functional requirements and sustainability requirements. The functional specification was the formulation had to be transparent in the blend. The solvent had to solubilize a hard to dissolve ingredient. The evaporation rate had to be in a narrow window of specifications, and the interfacial tension, the water-oil interfacial tension, was to be higher than a threshold. And also very important in cosmetic, but also in other areas, the solvent had to be odorless. The sustainability constraints have the environmental impact negligible or low, and the human safety parameters also negligible or low, according to the column model, the global harmonized system. So the most important thing here, let me say first, another constraint from the company we worked for this project was that they gave us an exclusion list. An exclusion list means their team, their R&D team, had already tested 24 solvent candidates, but no one was achieving the right efficacy, or they were not satisfying the complete set of the 7 constraints, the functional constraints, and then EHA's requirements. The cost is always an issue in terms of industrial use, and also we were told to be, to take into account cost issues, and so we started to look at the library, and we just made a feasibility study first, whether the library is appropriate to find optimal solutions. And when I say optimal solutions, means satisfying the whole set of functional variables simultaneously. So finding a chemical, finding a solvent out of the 300 or more solvents that fulfills the whole set of constraints, functional constraints. So we use a search algorithm that allows us not to predict function, because it is too complex, but allows us to do an efficient search in a library that contains several hundreds of possibilities of candidates, right? Now I am introducing here a plot where we calculate in our evaluation of the library whether it is appropriate to solve the problem. So we calculate what we call satisfiability probabilities, which is how probable is to find a chemical in the library that satisfies the whole set of 7 parameters. We will talk later on this probability, but let us advance. Let us advance through the example and say that so we measured in the laboratory certain parameters related to the solubility. So solubility of the ingredients was perhaps the tougher of all the requirements. but also the evaporation rate, the interfacial tension, which is related with spreadability, was an issue. And the way we work is by narrowing down the diversity, narrowing down to a small set of candidates, where we conduct even more complex or more cost experimental work. So that's a plot of approaching the targets, and this finally we could be able to find two optimal solvents that were successful, meaning that they were optimal in terms of function, and the environmental were sufficiently good in terms of human health and environmental constraints. Oh, this is a plot that let's say for the moment that the satisfiability probability we calculated was around 17%. So it was very low probability of success, and we will talk a bit more on this probability, on the mathematics of this. But that means how difficult is finding the solution, and it's a measure of how fitted. So if you find optimals with a certain library at such low probability, it means it has a very good fit for the particular problem, for solving the particular problem. Well, this is the summary. Well, we were able to solve one of the hardest solvability problems. The odorless and transparent solvent conferred very good spreadability to formulation, and we were able to reduce the health hazard, which was one of the main drivers for this project. Now, I would like to talk about a second project that where we use the solvent library, also in a cosmetic formulation. In this case, the problem or the request from the company was the replacement of a flammable solvent in a skincare formulation. So in this case, the solvent had to meet simultaneously 10 functional, regulatory, and EHS requirements. So you can see here everything from the solubility of the ingredients, turbidity and phase separation should not appear after the 3 freeze-thaw cycles, no crystallization, no discoloration at high temperature, good long-term stability of the solvent even at high temperatures. It had to be, this is a requirement that is more regulatory rather than scientific or technological. It should be INFI registered. This means it should be commercially available. Cost was also an issue, and human health hazard, environmental hazard, and also in this case physical hazard was the issue. Total 10 functional variables and EHS variables that had to be within narrow windows of the specifications. We had to find a solvent meeting that large number of specifications. Well, just a few slides on the details of the research. This was a freeze-thaw cycle. So it was -10 to 20, -10 to 20, -10 to 20. and after this cycle, no crystallization, no turbidity, nothing. It was stability. Stability was an issue at this point. So out of the larger library, 14 solvents were initially selected under the criteria of maximum structural diversity. You can see after the freeze cycle, we had all kind of behavior here. So we had transparency, which is the good thing to happen. We had solvents that caused turbidity or phase separation to appear, and also other solvents caused crystallization of the ingredients too. Now, the long-term stability test was 1,000 hours at 50 degrees, and no discoloration in this case had to happen. So we had no discoloration nor hydrolysis of the solvent would occur on such a test. And we had, you know, from the 14 samples, we had a diversity of results, which reflect the diversity, the chemical diversity that we used. So everything from yellowing, different shades of that yellowing. Also, we got hydrolysis of solvent in one case. So within the set, we identified an optimal solvent that enabled the formulation of the cosmetic product, satisfying the 10 functional specifications, and but also the results obtained with the first set of 14 allowed us to compute the probability of finding additional optimal solvents, possibly with better secondary properties, secondary characteristics. And this is an important thing. So you might ask, why did you start by a number or evaluating 14 solvents, right, in this case, and not 20 or 5? So the reason is because we figured out what are the probabilities, what are the loss probability governing the search, the process of searching chemicals that fulfill simultaneously the 10, in this case, the 10 functional parameters. And we know that by evaluating 14 solvents, we could be able to get a very high probability, like 75% probability, and that was good enough. But it would be the curve, the theoretical curve, indicated us that we could maybe find more solvents that were satisfying, that were optimal, and we proceeded. So we went to so we analyzed up to 47. So we add more solvents to the initial solvent set, and we set of 14 up to 47 solvents. So, and this is the 47, a collection of 47 that we evaluated. This is how it turns that we found finally 2 optimal solvents, one found in the first set of 14, and the other solvent, which was structurally different, significantly different, had the same functional performance, the functional state. So we end up with 2 solutions, and and we could find a better compromise in terms of efficacy and cost in this case. Another case that I would like to bring here is the metal degreasing. This is about metal degreasing. We wanted a replacement for trichloroethylene for the degreasing of sinterized metal parts. This is by immersion and ultrasonication, and so we had just a number of functional constraints, and again, so the goal was sinterized metal parts were extremely difficult for the degreasing, because these are porous metal materials. So you have the grease well deep into the pores, and it's difficult to degrease. And industrially they are using ultrasonication techniques. So we used the library. We found an optimal solvent. In this case, it was a levolinator. So we ultimately filed a patent of this application. And here you can see what happens when the efficacy of degreasing is not good. So the metal piece gets dark colored, and this is not good. Again, and here we could compare the satisfiability probability of the Inkemia library, the Inkemia solvent library, and compared to an analogous set of the same size of traditional solvents. So you can see the red dot in the middle of the density plot. Corresponds to a probability of 0.06, well, 6%, 7%, while the satisfiability probability of the Inkemia library was on this 65%. So in this case, we found three solvents with excellent removal efficiencies for the grease under ultrasonication conditions. The low vapor of the solvent will make them suitable for immersion or spray oven systems. The operating procedure involved the recovery, reutilization of the solvent, and it brought safety to the working place. That was good, and I think this is the last case I wanted to comment, and this is a marine paint formulation. In this case, the replacement. So the idea and the goal here was reducing the VOC content of marine paint formulation. So the strategy here was to select an non-VOC reactive diluent in order to replace partially the solvent endowment of the formula. Here the functional specifications were everything that matters in the paint and coating industry, which is and formulations, which is viscosity, film formation and leveling, the appearance, colorimetric stability, no yellowing, drying time, the hardness, the quality and the hardness of the coating once in the surface, the gloss, adhesion to metals and wood, and also chemical resistance. So we had to meet all those functional performances, and also health and VOC, the environmental health issues. Now here, just details of the experimental, and so we were comparing the formulation, the formula with the solvent, the traditional solvent, which was a white spirit, versus the solvent used by Inkemia, which was a reactive diluent. Here we can see how viscosity could be comparable. Also, the hardness was comparable and acceptable. The good film formation and leveling was observed. So the appearance of the coating was very similar to the benchmark. Same as the gloss. There's a little increase in gloss that could be corrected with mating agents. Like we were able to accommodate a deviation of the gloss by adjusting other ingredients of the formulation. There was a very good adherence and substrate according to the standard methods for measuring these properties, and also we found similar chemical resistance at the end of the evaluation project, and no yellowing was observed. So it had good stability upon exposure to the ambient. So here as it was not as easy as other projects with a probability of around 30%. So we were able to find one optimal ingredient. So that is the summary that we already have shown. And well, actually, this is an example from agrochemical. I think it's rapid enough to go through it. Here, the problem or the target was the replacement of aromatic hydrocarbons by non-VOC safer solvents. So in particular, we wanted to replace the Solveso 100, which is a mixture of xylene, toluene, and other aromatic hydrocarbons. So the solvent here had to be should display a good solvent hydraulic stability, because the emulsions and water, good chemical compatibility, emulsion stability, and all the functional properties like leaf coverage when applied to the crops, an active ingredient uptake, and should display selective phytotoxicity. So kill the bad plant, but not kill the crop. Also, the sustainability constraints, health, and environmental impact was considered. So the active ingredient was a class of the protoporphyrogen oxidase inhibitors. It's a class of herbicides, and so the company here, we collaborated with Isagro Ricerca in Italy. So they performed greenhouse experiments, but also field experiments. And here is the difference of when you treat the crop and without treatment on the right, on the lower right of the photograph. So the efficacy was very good, and here we had the probability of 63%. We could replace aromatic hydrocarbons with a long alkyl chain esters, specifically lactic acid esters, which is remarkably different, structurally different from the aromatic hydrocarbons, but it worked it worked nice, and the company filed a patent on the formulation. So it was an interesting thing. I would like just to finalize, just to make you aware of a little bit of our methodology. So we have talked about chemicals and functions. So for functions it's for the application chemist means all those things that we have already seen. In a cosmetic, formula could be everything from density, viscosity, stability, related to formulation, but also things related to the application, like appearance, applicability, rheology. In any industrial applications, you always find a relatively large number of functional parameters, which must be within bounds. So the thing is, how to keep the function, in a process of solvent replacement. When it is for the similarity principle, it is very probable that if you are using just one solvent, you are going to get many or one or more of the functional parameters out of specifications, right? You can do adjustments of the formulation in order to accommodate a new green alternative, but that not always works. And the basic message I would like to give you is to make sure you have the right diversity and the right size of your ensemble of solvent candidates to make the trials. I think that's the basic message. I don't want to go into much detail. Would like to finish at this point, and just to say that we have been introducing probabilities and statistical and probability notion, and this we have been able to understand profoundly these probabilities just by measuring all the functional parameters, even if we already know that one of the functional variables was out of specifications. So we continued measuring in our past research work all the functional specifications, and we were able to get a sense of what are the possibilities in terms of probability. To make a probability statement, you have to know what is the space of possibilities, the total possibilities, and then you can make probability statements. This is something we're not used to do, because in the application laboratory, once you know that a solvent does not fulfill an important functional variable, you discard it immediately. But you're missing information in order to make probability statements. So we try to understand all these probabilities, and this is the idea that just I wanted to bring to your attention, because I think it's important to have a good approach in terms of diversity, making being able to make probability statements. And I think this is all on my side, and probably I spoke too much today. I would like to pass the word to Laura and to the audience and I will be happy to answer any questions that might arise.
Great, thank you so much, Carlos. So yeah, that was a fascinating presentation. So for those of you, I do see a few questions have come in, but for those of you that have not submitted questions, please, if you do have any questions for Carlos, there is a question box off to the right-hand side of your screen. And if I could only get it to open, I could, there we go. Yes, so if you do have any more questions, please do submit them. So let me go with the first question. So as I understand it, your model predicts a set of workable or optimal solvent solutions. Can you synthesize all of them in your lab for bench testing for a client's lab application? So that question is just about, okay, so you have predicted there are many possible options, but are you actually able to synthesize those? Let's say you predict a really great molecule. Can you make it in your lab?
Yes, Lauren. Laura, yes, you're right. We can synthesize. We have capabilities and organic chemistry laboratories, and actually this is the job and the work we have done over the past decades. Is being synthesizing in collaboration with other laboratories, universities, chemical companies, in a number of projects. So we've been able to do a synthetic effort here, but also we are using existing chemicals that are excellent in terms of environmental health and safety. And we combine, the two sources. So our mission is to grow the largest possible green chemical library. In this case, we're talking about solvents. So that's our mission, and we are in a continuous effort on that direction.
Great. And actually, one of the next questions is a good follow-up question, I think, for that. So as you're working with the client, to solve a problem, once you identify a solvent solution for that client, and it's not commercially available, what are possible next steps? So certainly you can synthesize in your lab, but how would you make it at scale?
Well, right. This is an important issue that we have committed to try to develop all the required steps to make a commercial reality at large scale any optimal solution that we found in our work with companies. So the thing is, when a chemical is not commercially available, that means that you cannot have in your hands quickly. Now, what it means is, depending on the registration process of the chemical, depending on the manufacturing systems that are required, so it will take from 3 months to maybe 1 year, a year and a half to reach the market. I mean, what we believe is a chemical that is safe and that it works deserves the maximum effort. I mean, this is one thing, and we are committed to make commercial realities. Anything that we find useful and that it has very interesting sustainability properties. So in this direction we work. So we have a network of contacts in chemical companies, chemical manufacturers, everything from we operate own plants, like small plants for generating relatively small amounts of chemicals. That means we operate pilot plants on the 500-liter reaction scale. Also, we have contact with contract manufacturers, and we have industrial partnerships for future development of new chemistries.
Okay, great. Yeah, that's always a big question when you're developing new chemistries, but it sounds like you have a really good network to make that happen. So another question from another person that tuned in is asking about about using renewable chemicals. So they're interested in if the chemicals that you use are based on renewable resources, or are they petroleum-based? So I guess that's the first part of their question is, do you typically go for petroleum-based feedstocks, or do you have a preference for bio-based, or is that kind of more based on the client?
Yeah, that is so any source of good chemicals is good for us. So as far as you can have a well-defined chemical in terms of satisfying the environmental health and safety constraints, that is an amazing achievement. Whether it comes from oil or renewable origin, it matters to us because it matters to us as long as we can demonstrate that you have an advantage in terms of life cycle analysis. Like we have been in several projects on making products, chemical products out of renewables, and we've been performing a life cycle analysis, and it is not straightforward that you can get a good life cycle analysis from renewable. So there are renewable feedstocks where we have been able to have a good product with the right life cycle analysis. Sometimes this has not been possible. So we need to take care. But in over the past years, there has been in the green chemistry community a lot of effort to bring to market renewable chemicals, and for us it is an amazing approach if we can combine renewables, good life cycle, and good environmental health and safety properties. That will be the ideal situation.
Yeah, absolutely. I think that's the goal that many people are certainly striving for. That would be great.
Now we have just in this direction. I would like to that we are making lots of efforts to introduce in the libraries like algae oil derivatives. So we have found a source of very cheap algae oil that it's hard to believe because all engineers in the world tells you that algae oil is very expensive to produce, but we are now finalizing contracts with Asian partners that they told us that they found or cheap way to make that. So we're in a broad interest. We have all our antennas looking at whatever is coming from the renewables space, and hoping to introduce as much as possible into the commercial world.
Absolutely, and I think too, whenever you start from different feedstocks, then that gives you access to different functionalities and you know, maybe possibility for different structures that were not previously accessible. So certainly, I think it's a good place to go mining for new molecules. Another question that's coming in here, and I apologize because probably we won't be able to get to all the questions. I realize we're after the hour, so if we don't get to your question, I apologize. So I guess maybe this is a quick one, but is there information publicly available about the types of molecular structures that are in your library? Or, you know, what kind of information do you disclose publicly?
Well, it's coming. It's coming soon.
Great.
We have the you know, the tool. So we treat as an internal tool the whole library. But we are now in very soon we're going to make part of the library public. So you will have all the information. Even you can have access to physical access to getting the solvents and the chemicals, you know, from the internet. So we are very happy about that, but maybe it's not the moment to announce, because this is not official. Maybe I should stop talking, but the answer is yes. We are going to have a significant portion of the chemistries public.
Well, that's great. I will look forward to looking at that whenever it does become public. So another question is: have you found some traditional solvents to be acceptable, you know, screening through your column model? So some of the already existing chemistries, you know, have you found some that are already actually pretty good?
Well, yes. There are many. I would say. So you can have, for instance, dimethyl carbonate. You can have esters, fatty acid derivatives. There are not a good, you know, a massive amount, because you know the proportions of the low hazard in place. They are not the most abundant, but yeah, there are a number of possibilities. You will see when it's public that how many good options are commercially available. Maybe you are not going to find quickly a replacement for dichloromethane because of the unique properties, but we have been able to replace NMP in certain applications, such as reaction solvent for fine chemicals production. So, for instance, we have been able to replace N-methylpyrrolidone by a glycerol carbonate. You know, it's unbelievable how different are the chemicals, but they are bringing the same function. And this is an important concept when thinking about replacements. Think about the function rather than matching the physical-chemical properties. And I think this is the main message that we can give to the green chemist practitioner.
Yeah, absolutely. That's a very important message. That if you are looking for alternatives, obviously function is what matters most. So I think the last question we'll have time for today, because we're already 10 minutes past the hour, is kind of like a high-level question. But how does your lab inform or influence, if at all, a client's initial sustainability parameters, such as the scope or metrics of hazardous solvents? For example, in this relationship between the lab and client, who is it that's defining the toxicity?
Right. Well, many times, this is interesting. Many times we get the same question. So what is a green chemical for you? I have heard a lot of definitions, and people is sometimes we find that they are lost. I mean, a little bit on what to. So so we are totally systematic in this area. So so we have the global harmonized system. We want to have the maximum number of endpoints in the safe domain, and that's the most important concept. With being in general, our interaction with clients so far. So what we get is people want to have and to launch ambitious projects. So the ambitious projects mean, for instance, I don't want flammability. I don't want VOC. I want VOC exemptions. I want high evaporation rate. So the people is demanding very ambitious properties of solvents, and I think the challenge for us is to react to such ambitious demand.
Yeah. Yeah. Thank you. Yeah. No, I think that's a good point. Is depending on what they're asking for, sometimes it can be quite ambitious, but it seems like you have a really broad library to be able to address that. So unfortunately, we're going to have to stop with questions right now. We're almost 15 past the hour, so apologies again if your question didn't get addressed, but you're certainly welcome to contact us, and we can put you in touch with Carlos to ask any follow-up questions. So I just wanted to announce just really quickly an event that the GC3 has going on in Boston. This will be the day before the Green Build event. We have a networking event the evening before, which is at the UMass Club on the 32nd floor in downtown Boston. So it's got great views of the skyline. And so at this event, so this is focused on the building product sector. So we'll be bringing together GC3 member companies and others interested in green building products. And part of the event will actually feature some startup companies talking about their companies and technologies that have applications in the building sector. So if you do plan on coming to Green Builds, please feel free, if you're interested in attending, please email us at gc3info@greenchemistryandcommerce.org. So I just want to say thank you again for joining us, and thank you so much to Carlos for speaking. I really enjoyed learning about the fascinating combination of math and computational chemistry and statistics that Inkemia uses to try to find green chemistry solutions for many different applications. So again, thank you, and have a great afternoon, everyone.
Thank you very much.